Before starting today's class, so I will explain about the first lab assignment. So I posted. Oh, can you hear me? Hi guys. The students joining. Can you hear me? Okay. So I posted the first lab assignment on the Blackboard, and then actually this lab assignment is the design lab. So that means that the final goal of this design lab is to implement the simple pipeline risk file processor. So, and then I made several lab assignments, and then I believe these labs are helpful for implementing the pipeline processor step by step. So I believe most of the students took the digital design course, so it's digital logic design course actually, and then I believe most of the students have experienced the So I believe the most students have used some EDA tools such as the Model during this technology design course. But so unfortunately, the digital design course is not a mandatory course in the computer engineering department. So some of you, I believe some of you did not use this EDA tool. So I prepared how to install this ITI simulation tool called COSE222 in the first lab assignment. So if you read this first lab assignment, I believe I explained very kindly. So actually, the bad thing is that this instruction changes every year. So actually, this is not a free tool. So which means that you need to purchase a license not to use this tool. It's not free. But Intel, so very big CPU company, generously provide this free version of the COSE222. But it requires a license, actually the free license. And then I set up this free license on my license machine. So actually you need to install this COSE222 EDA tool on your own laptop or desktop computers. And then you need to also set up the license environment not to use this tool. So please read thoroughly this document, and then so I believe I explained how to install this COSE222 very kindly. So you can follow these instructions. Okay? And then actually the first assignment is to make very simple project, and then so in this project you are requested to design a very simple logic gate like exclusive OR and adder or subtractors. Also, in order to simulate your design, actually in order to verify your design, you need to simulate your design with the test bench. So actually in this document, I provide example code of ending it and 2 called end2, and then you can see you can find the 2 input signals and 1 output signal here, and then also I provide the test bench for this end2 module, so like TB on the bar end2. So this is the example of test benching, and then using this design module that called the end2, and then the test bench module called TB on the bar end2, you can simulate your design, which means that you can verify your design. The verification is that you need to check, verification means checking if your design works correctly or not. So actually, you can check the waveform of your design with this test bench, and then also you can check if your design works correctly or not with this waveform. And then these are assignments for you, and you need to submit your code, and then it's a very simple report that shows the waveform of your design. Okay, and then also also, I posted several resources for digital system design. So you can find the system variable tutorial. So this is not a document. Actually, this is the link for the tutorial site. And then I believe some of you are not familiar with the system variable or variable. So which means it's a hardware description language. So actually the syntax of the variable it's a very famous hardware description language. The syntax of the variable is very similar to the C. So if you are familiar with C, so I believe you can easily write the code with variable. And then system variable is actually the enhanced version of the variable. So if you are not familiar with this system variable, and you can visit this tutorial site, like a system variable tutorial. And then I think this site is very good. So you can visit this site. Also, I posted several lecture notes regarding the variable design and then variable test bench design. So in this slide, so I will not explain about this variable design. This is because this is not this is not a topic which will be covered by in this course, but you can read this lecture note here and then try to study by yourself. And then another document is the variable test bench. So actually, in order to simulate your design, so which means in order to verify your design, you need to also write test bench. So I also made a lecture note for writing test bench in here. So I can read this note, slide note here. So actually, these notes like Verilog or test bench slide there, it is made for Verilog design, a system Verilog. But system Verilog is very similar to the Verilog. And then actually, the Verilog is the subset of system Verilog. So if you write the Verilog code, so it will work correctly in the simulator. But I posted a document that explains the difference between system variable and variable here. So we can compare some differences between system variable and the variable here. So if you are not familiar with the system design, then try to start early the design and assignment. Okay, so actually the due date of deadline of this design lab is the maybe next not coming the next Friday, not this week, but next week, so April 22nd. But if you are not familiar with this value, actually the first lab assignment is very simple. But if you are familiar with this so value of design, I believe you can complete this assignment within 1 hour. Actually, less than 30 minutes. So actually, the size of the quest is very large, because that means the file size. So it will take time to install the quest actually. But for this lab assignment, if you are familiar with the value of design, it will be taken less than 30 minutes. Okay, but if you are not familiar, you are not familiar with the design and try to start this lab assignment early. Okay. Any question? Okay.
Since I use a MacBook,
unfortunately, you cannot install the distro on MacBook.
I use compare the red with my terminal, and then I use different voice interface. Is it possible?
Yes. So you can connect.
I use a different software.
Different software. So can you use another software, like another simulator?
Yes.
Actually, oh, is that possible? It's okay. So you can compile your design module and then you can verify your design module with the other simulator. It's okay. Okay. So let's get started with today's class. So in the previous class, we learned about how to build the simple arithmetic units such as adder, subtractor, multiplier, and divider. So I will explain again for this design. Then, so actually, these very simple arithmetic logics. I believe these arithmetic logics are covered by some logic design course. Okay? So I will cover this implementation in detail. And then, so let's learn about the floating point today. Okay. So floating point means soso in Korean. So until now, we learned about integer instructions. So which means that these instructions just handle integer data. So integer type data. So which means it's a terms type data. Okay, integer type. But floating point is the different type. So actually, in a real world, the integer type number and then floating time numbers are different. But we can apply the same arithmetic operations for these different type of numbers in the real world because we are very familiar with the arithmetic operations in the real world for the integer type data or floating point type data. Actually the same, so we can apply the same operations for these different type of numbers. The only difference is that the floating point operations are a little bit more difficult than the integer type operations. But computer is a computer machine, a computer hardware. Floating point number is totally different from the integer type number. But if you learn how to represent the floating point number in the computer system, I believe you can easily understand how to represent these floating point numbers in a computer hardware. Okay. So let's start from the real numbers, like the real decimal numbers in our real world. So how can you represent the floating point number in the real world? Okay. So how can we represent? So we can represent a floating point number like the 2.3 or 123.9, like this. If we can find this floating point, then these numbers are floating point numbers. And then we can easily represent these numbers like real numbers with the floating point number. But there are two different types of this floating point representation, which means that we can represent the floating point number with the normalized form, or we can represent the floating point number with the non-normalized form. Yes. So what is the normalized form? If we represent the floating point number with the normalized form, which means that this floating point number has got some base, and then some point here, and then number has the fraction part. But we can find only one digit for this base, and then this number is multiplied by power of 10. Also, this power of 10 has the exponent, this number, right? Plus some numbers or minus some numbers, exponent part. So that's how we represent the floating point number with the normalized form. If there are multiple digits in this base number, then this means that this number is not normalized. So normalized means that this number, the fraction part, has the only one digit of base. So, and then this is same to the binary number, the binary floating point number. So we can represent the binary floating point number with the normalized form, which means that this number has the base one digit of the base, and then point, and then some fraction part here. And then, so we can say that if the normal, so this fraction part has started with some non-zero number, with some decimal floating point number, the non-zero number, then but we can say that this is the normalized floating point number. But if this fraction part starts from the zero, starts with the zero, and we can say that this is not normalized form. So how about the binary number? It's binary number. So normalized form means that this part has only one digit, and then this part, the base part, does not have zero. So which means that this part has only one digit non-zero number. Then the binary number, non-zero, one digit means just one, the binary number, right? And then we can find the point here, and then we can have fraction part. So this part is called fraction. And then this number is multiplied by power of 2. Here. So this is the binary number. So its base is 2, and then also we can find the exponent here and here. And then also floating point number has positive numbers or negative numbers. So we require sign in terms of this floating point number. So which information is required? So in order to represent floating point number, we require sign. Sign information, so it represents the plus or minus. And then, so 1 is always 1, it's a normalized form. So it should start from 1, and then we need this information. This is the fraction part, okay? And then, so base is the 2, the power of the 2, so we also require this part. This part is called the exponent. So in order to represent the floating point number, we require 3 different information: sign, fraction part, and exponent part. So actually this floating point number representation is defined in IEEE standard. And then IEEE standard defines the float type. Actually, this is called the single precision floating point number, and then double type, which means the double precision floating point number. And then this single precision floating point number occupies 32 bits to represent the sign, fraction part, and exponent part. And then double precision floating point number occupies 64 bits. Okay, so that's why it's called double. And then this 32-bit single precision floating point number is called float type in C. Okay, so as I explained, this floating point representation is defined in IEEE standard, and then there are 2 representations, like a single precision and double precision. And the single precision occupies the 32 bits of binary data, and double precision occupies 64-bit binary numbers. So let's see how to represent the floating point number with the binary data. So I already explained that we require sign bit, and then exponent part, and then fraction part. And then there are 2 representations. So actually we require only 1 bit for the sign, because we have only plus and minus, and we represent the plus and minus with the 1 bit. And then how about the fraction part? For the single precision number, the fraction part has 23 bits. And then for the double precision number, the fraction has 52 bits here. And then for the exponent part, the single precision requires 8 bits, and then double precision requires 11 bits. And then this equation shows how the floating point number can be calculated from this binary form. Okay, so if we see this equation, we can find, oh, this is the sign bit, so we can represent the sign of the floating point number like this. And how about the fraction part? So I already explained that fraction part is the 1.xxxx, so this part. So this fraction, the fraction part is just to represent this part here. And so which means the 1 plus fraction. And then exponent is represented like this. So actually, if you see the this exponent part, you can find that exponent has positive numbers or negative numbers. And then in the integer type, so we already learned that we can represent the plus and minus integer type using 2's complement numbers. But in the floating point number, the exponent, we can represent the exponent, and then how to represent the exponent is different from the 2's complement number. Okay, so how can we represent the minus, which is the negative number with the 2's complement number? So with the 2's complement number, we can represent the negative number like minus negation of the some positive number plus 1. This is the negative number, but this exponent part is different. The exponent part is calculated like this. The exponent is number, and then this number is subtracted by bias. So actually, which means that exponent part has only positive number. Also, the bias is the positive number. Okay? And then for a single precision number, the bias value is the 127. And then for the double precision number, the bias is the 1023. So that is the actually, oops. John is not working. Sorry. Sorry for inconvenience, but I think the John is not working. I don't know. So I think the Wi-Fi network is not working here. Probably. Sorry about that. So Zoom was disconnected for the inconvenience. So okay, let's resume the class. Okay, so I explained that the exponent part has the positive number, and then we can calculate this part like exponent minus bias. And then I mentioned that the bias is so you can find that exponent for the single precision number, the exponent part has the 8 bits. So which means that this number can have from 0 to 255. So 127 is approximately the half of the maximum number. So actually it's like 2 to 8 divided by 2 minus 1. So that is the approximately half of the maximum number. So for the single precision number, the bias is the 127. So which means that if the exponent part has number 0, so which means the exponent part has actually 127 for the single precision number. Okay, so you need to remember that. So in order to calculate this exponent part, the exponent part is subtracted by bias. So bias is also some defined constant number. The 127 for the single precision number, and then 1023 for the double precision number. Okay, that's how to represent the floating point number in the binary number system. Then, so actually, if we just focus on the dispersion part, so we can say, well, we already know that we can represent the dispersion part like a 1 point x, 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 x. So which means that the magnitude of this part is equal to the 1.0 and equal to or bigger than the 1.0, but this number is smaller than the 2.0, right? So that means that the maximum number for this part is approximately 2. Then, so actually, I already explained that the exponent number has from 0 to 255 for the single precision floating point number. But actually, all zeros or all ones are reserved. So if the exponent has the all zeros or exponent has all ones, this number is used for representing some specialized number. So actually for the normal number, so we use the exponent from 1 to 254 for the single precision number. Okay. Then what is the smallest value? So what is the smallest? So that means that the magnitude is the smallest. So for the smallest value, the exponent is the 1. So actual exponent is the 1 minus bias, so which means the minus 126. So which means that it's 2 minus 126. And then how about the fraction part? For the smallest number, the fraction part should be all zeros. So which means that 1.0000. So actually this is 1. So which means it's actually 1.0 multiplied by 2 minus 126. It's approximately this number. It's the smallest value. It's the smallest, it's a magnitude is the smallest. And then what's the largest value? So I said for the normal floating point number, the maximum number is the 254. So which means 1110. We can calculate the exponent like this. So which means that so put 127 multiplied by 1.1111. But it's approximately 2. So it's approximately 2 multiplied by 127. So this is the largest number which can be represented using single precision floating point number. And then also we can calculate the smallest value and the largest value for the double precision floating point number. And then like the single precision floating point number, all zeros and then all ones are reserved for exponent. So which means that the double precision floating point number, the smallest exponent is also 1, and then the largest exponent is, I need to check. 11 minus 2, right? So this is the smallest number which can be represented using double precision floating point number right here, and this is the largest value. Okay, so we can easily calculate the smallest and the largest values based on the definition of single precision or double precision floating point number. Then, So, and then let's see the relative precision. So precision, so actually, we can use floating point number to represent the real number. But, we cannot represent the 1/3 with the decimal floating point number. Why? Because this is the 0.33333 infinitely. So actually we can represent this real number with the approximately. So and then that's also same to the binary floating point number. And then actually, the precision of the floating point number is determined by the precision of exponent part, like 2 to this part, the power of 2. And then it's also same to the decimal floating point number. The precision of the decimal floating point number is determined by exponent part, like 10 to some numbers. It's also same to the binary number. And then how about the single precision floating point number? That means that precision of a single point floating point number. It's approximately 2 to minus 23. Okay? Because sorry about that. So actually, sorry. The precision is not determined by exponent. It's determined by fraction part actually. So which means that we can so precision means that how can you represent the number precisely. So which means precision is determined by actually fraction part. Sorry about that. So actually the exponent part decides the maximum value or minimum value of the number. Okay. Then actually the precision is determined by fraction part. So for the single precision number, the fraction part is about the smallest precision. The smallest precision is the 2 minus 23. So and then approximately, if we just calculate the approximate number with this 2 minus 23, and then it's equivalent to the 6 decimal digit. So which means if we just use the single precision floating point number, then it's equivalent to the 0.00000 this precision with the decimal floating point number. And then for the double precision number, so it's about the precision is about the 2 minus 42. So this is the 16 digit decimal digit of precision. Okay? Actually, this is so. Actually, for the single precision number, so precision for the decimal number is not small, so it means that we can just represent the 6 digit, okay, with the single point floating point number. And then let's see the example of the floating point representation. Okay, so how can you represent the minus 0.75? So this is the decimal number. So how can you represent this number with the floating point number? So the binary floating point number. So if we see that this number, then we can find that for sign B is the minus. So as is, so sign B is just 1. And then it's very simple. And how about the fraction part? So the 0.75 is the 1.5 divided by 2, right? So which means that 1 plus 1/2, and then divided by 2, which is equivalent to the 1.2 minus 1 multiplied by 2 minus 1, right? So it's 1.1000 multiplied by 2 minus 1. Okay, so What is the fraction part? So fraction part is easy. It's the 1, 0, 0, 0, 0 here. Because the first digit is always 1. So you just ignore this part. So fraction part is the 1, 0, 0, 0. And how about the exponent? So real exponent is -1. So then this is the some exponent minus bias. And then for the single precision number, the bias is 127. So the actual bias for the single precision number is the 126 for the binary floating point number. So this is the exponent part, and then this is the fraction part, and the sign bit is the 1. And then we combine this information, then we can make the single precision floating point number like this. Sign bit, and then this is exponent part, 8-bit is exponent part, and then fraction part. And then double is the sign. The fraction part is the same, actually same. The number of digits is larger. And then also we can represent the exponent part using the bias of double precision number. And then the reverse operation is, so we can also think about the reverse operation. So we can represent some decimal floating point number using this binary floating point representation. So like this. So if this number is the single precision floating point number, and the first digit is the sign bit, and then the next 8-bit represent the exponent bit, and then the remaining bits are fraction bits. Okay, and then we can split these numbers like this. It's a sign bit, and then this is the fraction part, and then this is the exponent part. Exponent part is the 129. So because this sign bit is the 1, this is the minus number, and then this is the fraction part. So which means that 1.0100000. Then multiply by 129 minus 127, which is 222. This is the minus 1.25%. Because it's 1/4. Multiply by 222. So minus 5. Okay, actually, this operation is easier than this operation. Okay. And then, so let's think about some reserved number. So in the previous slide, I mentioned that if the exponent numbers are all zeros, or if exponent numbers are all ones, these numbers are reserved. So actually, in order to represent the normal floating point number, we use the exponent numbers from 1 to the maximum number -1, like all ones -1. And then let's think about some specialized number. There's a special some number. So, and then these numbers are called normal numbers. So which means that, this number is not a normal numbers. Okay? It's for the normal numbers. So let's think about the exponents are all zeros here. So in this case, if the all exponent numbers are all zeros, and then we use these numbers for representing very small value. I said very small, not small number, small value. So that means that the magnitude of this number is very small. Okay. So what does that mean? So it means actually the sign bit is the same. So we can use the sign bit to represent the sign of the numbers. And then, but if the exponent numbers are all zeros, then which means that this part starts from 0, not 1. So if this part starts from 0, so which means that the value of the magnitude of this part is very similar to the 0. So it's near 0, right? Because it starts with the 0. And then there's the fraction part. And then how can we calculate the exponent? So exponent is just the 1 minus bias. Okay? When if the exponent bits are all zeros. Okay, so it's the minus bias plus 1. So which means for the single place number, so which means that this is the minus 126. So if you see the this equation, then we can find that for if the exponents are all zeros, and the value of this number is a very small value, has a very small value, which means that the magnitude is similar to the zeros. And then if the fractions are all zeros, and then exponent is all zeros also, then which means it's 0. So, right. The exponents are all 0. Okay? And then fraction parts are all zeros also, which means that it's a 0 plus 0. So this is 0. But interesting is that actually it's the same to the decimal number. So we can have two different zeros, like a positive 0 or negative 0. It's actually the same. But it's also same to the binary number. So actually, for this 0, the sign bit can be 1 or 0. So which means that 1 0 0 0 0 0 0 0, which is also 0 for the floating point number, and then 0 0 0 0 0 0, which means also 0. So this is the minus 0, and this is plus 0 for each. Those are all zeros. Okay, so there are two different forms of number 0. And then if the exponent has all ones, which means the exponent bits are all ones, and then we can use this number to represent the not real number, which means it's a not number. So, for example, if the exponents are all ones, and then the fractions are all zeros, and then we can use this number for representing infinity. Okay, so it's a very large value, but we cannot represent this value with the computer. But what we can represent the infinity is specialized number. Also, all exponent bits are ones, and then fraction bits are not zeros, and then we can use this number for representing not a number, and then it's called none. It's called then. So which means it's not a number. So you can find this number sometimes in our C program. So if we if our C program generates some wrong number, such as divided by 0, then our C program may return the not a number. And then, so actually the computer hardware used this specialized form to represent the not a number here. Okay? So it's a literal or undefined number in the computer system. Okay. So actually, so if you remember how to represent the floating point number, actually this is the specification. So it's just a rule. If you remember the rule of how to represent the floating point number, then we can easily, you can easily convert some decimal floating point number to the binary numbers, and then also vice versa. And then let's see performs the arithmetic operations using floating point numbers. Actually, when I explain about the integer type arithmetic units, and I start from the decimal arithmetic operations, because it's the same. The binary arithmetic operations are the same to the decimal arithmetic operations. The only difference is that the base number is different, just different. You can use the binary base, the base of 2, or you can use the base of 10 for the decimal number. And then the floating point number is floating point arithmetic operations are also similar. So let's start from the decimal operation. Then how can you calculate the floating point addition? Like here. So this example shows that 9.999, particularly 10 to 1 and 1 point. So this addition operation. Then how can you calculate this decimal floating point number operation? So first, we need to align the decimal points. So if we see that these two numbers, we can find that all exponent parts are different. Then, but these two numbers are normalized form. So the first thing we need to do is align exponent parts. So make the exponent parts the same. So align the decimal points. So which means that we make the same exponent numbers. Okay. So this number is changed to the 0.016 multiplied by 10. And then if these exponent parts are the same, then we can perform the add operation. So add for the significant. So we can perform this one, but if you know this part is not normalized, the significant part is not normalized. So we need to normalize the significant part. And then additionally, we may need to run or renormalize operation for the final result. So which means that we just take some number of digits after this point. That's how performs the arithmetic operations for the decimal floating point numbers. And then it's the same to the binary number. Then how can we perform the addition for the floating point numbers? So this is also the example. So you can find that all exponent parts are different. The first, we need to align the binary points. So which means then make the exponents the same. And then if these exponent parts are the same, we can perform the add operation for significant. So then we can perform the add operation and then we just normalize the result. And then this is the sum. And then the binary number has a fixed number of digits, so we need to also check the overflow or underflow of the final result. And then we can also apply the one or renormalize operation if necessary. So actually the same. So these 4 steps are required for performing floating point addition. But what is different? For the integer number, the hardware structure of the adder unit is very simple. Okay? We can just so we can just include some very simple full adder logic for each digit of the adder, each digit of the adder unit. But for floating point addition, we require the 4 different steps. So which means that not performs the floating point arithmetic operation, the hardware structure should be more complex than the integer type hardware unit. So that's why the floating point units are called the FPU. And then actually we will learn about the ALU or integer type, actually the integer type ALU in the chapter 4. But if we just apply the FPU, and FPU consume actually more cycles than integer type arithmetic units. Okay. And then how about the, so this is the structure of the hardware floating point adder. So actually this floating point adder implements the 4 different steps of this floating point operations. And how about the multiplication? So this multiplication we just performs the exponent part. So you can just add the exponents, and then we performs the multiplication for the 2 different significant here. And then we performs the normalization, and then round operation, and then sign is iterative. So actually, if we just compare this floating point multiplication with the add operation, then we just, this part is just different. Actually, the sign part is very simple. So we can just check the minus sign or plus sign of the 2 digits, 2 numbers. But only this part is different, like multiplying of the significant. So it's same to the floating point multiplication. So it's a line for the binary. So we just add the exponent, multiply, normalize, normalization, and then round. And then we just calculate the sign bits. Okay. So actually, this is the pure multiplication. So this is similar to the multiplication of the integer type. But for this floating point multiplication, it also just requires these 5 steps. But the last step is the very simple. So it's very similar to so 4 steps of the floating point add operation. So what I want to say is that for addition or subtraction or the multiplication and division of the floating point number, the complexity, the hardware complexity of the adder or subtraction, addition or subtraction, and multiplication or divisions are very similar. So actually, we require different steps, like some line of the exponents, and then some addition or subtraction of the significant, and then also normalization, and then round operation for the final result. And then actually, these steps are also required for the multiplication or division. Only this part is different. Actually, this part is very simple. We can just apply the add or subtract operations for this exponent part. So, the complexity. The hardware complexity of addition, subtraction, and multiplication and division of the floating point numbers are very similar. So which means that for the floating point number, the floating point add, it may require more cycles. Like for example, 5 cycles with hardware. And then, which means for the multiplication, floating point multiplication, it will also require similar cycles, similar number of cycles, like 5 cycles, because the hardware complexity is the same. But just remember that the floating point hardware is more complex than the integer type hardware, and then it will consume more cycles. Okay? So I want to explain this. So actually, in this course, we will learn, actually in chapter 4, we will learn about how to build RISC-V processor. So which means that you need to understand how to build hardware, like some this arithmetic units for the RISC-V processor. But in chapter 4, actually in this course, we only cover the integer type processor, not floating point type. So actually the processor structure is very simple, and then actually the execution part. So execution part just includes this hardware, arithmetic units or arithmetic units actually. And then this execution part is also simple. And then it will consume only one cycle because we are just assuming that our processor handle only integer type data. But you know, normal processors support also floating point data. Right. Again, the floating point data is very, very important. So it's widely used for our normal applications. So our normal CPUs support also the floating point data, which means that not to calculate the floating point data, our CPU will consume more cycles, which means that our CPU structure will be more complex. Okay. But this complex process architecture will not be covered during this course. So I think actually this advanced process architecture will be covered in the advanced course or the undergraduate computer architecture course or the graduate course. Okay. So and then let's see the floating point instructions in RISC-V. And then, as I explained in chapter 2, we are learning about the RV64I. So I means the integer type processor. So this is the baseline processor architecture for handling only integer type data. And then if we can extend this RISC-V processor with the F option. So if we include the F after this 64 RV64I, then which means that this processor supports the floating point type instructions. Okay, so basically all processors need to support integer type instructions. It's a baseline. And then we can add the floating point instructions with the F option. And how can you implement this floating point with type RISC-V extension? And then I firstly mentioned that the integer type data are totally different from the floating point type data. So you can think like this. So it's an integer type data, and then floating point type data. So this is the basic data. So this data is handled in general purpose, some integer type general purpose registers. So like X0 to X31. But not to handle the floating point data, RISC-V supports the dedicated floating point registers called from F0 to F31. So these registers are dedicated floating point type registers. So which means that floating point type data is just stored in these registers from F0 to F31. So which means, so you can think like this. So in chapter 2, I explained, oh, this is the register file, and then actually some arithmetic instructions and then logical instructions access the data in this register file. This is the memory. So actually, the data transfer between memory and register files are handled by load and store instructions. So integer type load and store instructions. And then in order to support the floating point instructions that I mentioned, we require the additional register file or floating point from F0 to F31. So which means, so actually the basic instruction just handles the data in this integer type register file. And then we have additional register file called the floating point register file. So which means we require additional instructions that handle data inside of this floating point register file. Okay. Also, the floating point arithmetic unit is totally different from the integer type arithmetic unit. I already explained that the hardware complexity. The hardware structure of the floating point arithmetic operation is very complex. So we require the dedicated XPU just to handle the floating point data. So RISC-V supports the additional floating point instructions. So like F add or F more. So this is the floating point addition or floating point multiplication instructions. Also, RISC-V supports the floating point load and store instructions. So what does that mean? So FLW or FLV, this is the floating point load, just hands the data transfer from memory to floating point register file. Okay, so we require the dedicated instructions for handling floating point data. Oops. And it's the same to the arithmetic instructions like here. So you can find the FF, FSUM, FMO, FD, and also FSpot. So it's a square root. And then also by adding postfix at the point, then we can distinguish the single precision type data or double precision type data. Like if the postfix is at S, so which means that for this instruction just handles the single precision floating point data. And then if the postfix is the .D, which means that these instructions handle double precision floating point data. Okay, so we can have the comparison instructions and then so some branch or jump instructions. Okay. And then this is the example code. So this is the example function that handles the floating point instructions. And this is the example code. And then actually, it's very similar to the integer type instructions. So the regularity is very important to build the instruction set architecture. So same rules are applied to the floating point instructions. Okay, so this is the floating point load and the floating point load. Yeah. Actually, the format is the same, but only the floating point registers are handled by floating point instructions. Okay. Okay. So then, as I mentioned, these floating point representations are defined in IEEE standard. So actually, the IEEE standard defines some very detailed representation of the floating point instructions. But the hardware cannot implement all specifications, so all things specified in this IEEE standard. So we may apply some trade-off between the hardware complexity or hardware and the precision of the floating point operation. I will skip this one. Okay, now let's check the some frequent mistakes in the binary numbers. The first mistake is that right shift. So we can apply the right shift for the division operation. Like if some numbers are divided by power of 2, or pretty much power of 2, like some multiple of 2, like 4, then we can convert this operation using the right shift right. Okay, so if a certain number is divided by 4, then we can easily implement this operation by shifting 2 digits to the right. Well, but it can be applied to the positive number, but it cannot be applied to the negative number. So this is the example. So this is the this complement number is negative number minus 5, and then we apply the shift right 2, and what is the final result? Final result is the minus 2. So actually, the correct answer is minus 1 for this division operation. So if we want to apply the shift operations instead of division, then we need to check actually the sign of the dividing. Okay, so it's a frequent mistakes in the operation. So then another mistake may occur in the associativity. So this is caused by precision in floating point number. So what does that mean? So actually the associative rule is very very obvious. So actually we already know that, oh, this equation is the same to the right equation. Actually it's the same, right? But in a computer system, the result may not be equal, right? So let us assume that this is the x, this is the y, and this is z. And then we can know that, oh, this is the very large number because the exponent part is very large. And so, and then this is the minus number, and then this is the plus. So what does that mean? If we just first propose the x plus y, so you already know that, oh, this is the 0. Because the sign is different, but the magnitude is the same. And then plus z is 1. So the final result is just 1. So correct answer actually. How about this one? Because this y is a very large number, if we just propose the y plus z first, this number is the same to the 1. Because even though 1 is adding to a very large number, the result is also very large number. Because of the precision, limited precision. So this is the result of this operation. And then actually, if we perform the x plus this operation, then final result is 0. So what does that mean? Because of precision, and then actually the associativity should be maintained in our equation, but in the real computer hardware, based on some order of operation, then the final result can be different. Okay? This is mistake. Okay. Yeah, so I will stop here, and then in today's class we covered how to represent the floating point number in the computer hardware. Okay, and then in the next class we will move on to chapter 4, the process of design. So this is actually a very important part of this course. So then we cover. Amen. Question? Okay. So see you in the next class.